Inez, can you hear us?
Yep.
Okay, cool.
Right here.
Is okay. It's not echoing.
I think it's just
Is it echoing? Can you hear me? I just want to make sure Inez is out there. So. Yeah, okay.
You want to check? I think it's just picking up like water. Noise right now.
Right now it's in the city.
I could definitely hear when you were talking them loud. I'm just which is fine.
Okay, I changed the where it's picking up the audio. I'll try that. Out there.
I didn't have a call weekends. It was. I didn't sure like withdrawal. Yes.
Okay, hello. Can you hear me? Just testing, just talking. I'm sure you guys can hear me. If I walk.
That sounds really good on this thing.
Okay.
Yeah, I just think it's actually shocking how much it picks up of all this. Like you can literally pick out Jaden's voice.
Oh, really? And it was still doing that right now. And then I changed the where the microphone is coming from.
It was a little bit better, but it was more like I was surprised. And they're all
yeah,
because they're talking good audio. I think last time we just had is we were sitting, we could hear an echo in the room. So it wasn't a Zoom. It was in the room. But right now it sounds all fine, right?
Yeah.
No, I will.
So maybe last time this wasn't off or so. Keep talking. I'll listen from here.
Okay. Yeah.
Please.
Okay. Can you hear me? Or do you want me to like speak louder?
Do you hear that?
How? Do you hear echo at all? Is there echo? Anywhere? If I turn the
Bad.
hello? No? From the like the
So what did the science schools getting well? When I tried to I'm saying it's usually I don't have her on there.
yeah, then I have it on YouTube already connected. Yeah. Working. It was working.
But I have to click somewhere in your mouth.
Plug it back in.
Because I heard that the clicks, so I might just really have to put the mouse in the slide for it to work. And then mouse see if it works. Yeah, sometimes it does that.
Okay, cool.
I think it is. It definitely, it looks like it progresses a lot better. But I'm all set. Not too bad. I can't. So it's like. You know, it's thrown a lot of time, so it's a good access, so I usually just listen to, I think just listen to music or think about that to. Well, like, I'm stressed out, that is, how. And then not saying less. Interesting, I guess. She's not also, I was see brand point here, it's we need to be a man. Like, I listen to it's way too much to me what her name is personally that's Harrison, but.
It's right there, we'll see.
What you're like, nobody really wants cheese.
Yes. Yes.
You have to say something. Yeah. Yeah, nobody's posted after too, so like you know, it's just. Yeah, I go, you know, I go back and I just have a nice life. Like 5. You know, just saying, I was like, so far. And so there's some comfortable. So to. I kind of just reason I felt she's able to eat away. That's no one can ask. No, I every time you start, I show them, okay, it's a good chapter, but. It's a good second. Yeah, it's a week. Baseball. Just maybe, yeah, so you're watching your team's your team. She, I'm not gonna use, do you want me to go off? I feel bad, that's. Yeah, she was like concerned, she comes out to you like. Yeah. And you're like, no, like. And that can make me, yeah, it'll make me lose can and it'll have some. I always. I totally get her. Yes, her surface. No, it was, it's made it probably was played. Hey, I got it, I marked it, don't watch that. It's not showing up. Okay, yeah, try not to. And it's good. I think it's fine. That's not. Yeah. Okay. I think we just don't be famous, yes. Yeah. Yeah, so then we have a lot of stuff that's going on. There's a city. There's like the Spanish there's no booth. So that's not gonna be done until spring. Yeah. Yeah, I saw. Nice. More than you have. What is this stuff that basically? And then there's yeah. It's actually not ATX, but
No, they should be able to hear you.
So there's gonna be
And then this works. Yeah, Ines tested it out there, standard, we'll see, I think down is next page, so. Good, and then 5 minutes or so, we usually start at 9:50.
Yeah, that's great.
Yeah.
So at least I don't think there's any plans for that. Hang out more from the heat. So there.
The audience is on.
That. I just asked it, it's gonna be on the order of my head.
Start in the minutes.
Yeah. It's kind of easy. Moving, gives us all. Here's my thing, okay? So.
Yeah.
So.
And then I brought the,
I also I am the artist of most like 5 6 so far, I made each thing like there is a way to make this thing. See how long the money is. All I can bring you substantially. Houses, so this thing. Is there money in space? There are here. So there's just and yeah, I was saying our conference just use this. Is the way like that. What the scale? It's like it's obscure. So I was usually if you already have similar result. You just
Alright, I'll just start a little early, but I want to introduce our speaker today, Dr. Dan Wasserman. Right, he's a professor in the electrical engineering and computer engineering department at the University of Texas at Austin. He received his PhD in electrical engineering in 2004 from the University of Princeton, where shortly after he started his teaching career in the physics department at the University of Massachusetts, and then moved to the electrical and computer engineering department at the University of Illinois Urbana-Champaign, and then is now where he's at the University of Texas at Austin. He has also been recipient of the NSF Career Award and the AFOSR Young Investigator Award, and has also been recognized as a distinguished lecturer by the Institute of Electrical and Electronic Engineers Society back in 2017. So if you would help me give him a warm welcome, and I'm excited.
Thank you so much for that introduction. And thank you so much for inviting me here to lovely Flagstaff. It's a real pleasure to be here. I've never been here before. So I drove up late last night and I was watching out for elks, but I actually couldn't see much of anything. And then you sort of wake up in the morning and there are these gorgeous mountains that just appeared. It's incredible. So I'm going to talk today about my group's work, engineering optical response at spatial and temporal extremes. Before I do that, I do want to sort of introduce you to, first of all, my research group. So I lead the mid-infrared photonics group at UT Austin. And if we were sort of forced to have a mission statement, I suppose it would be something to the effect of that our group designs, grows, fabricates, and characterizes materials, devices, and structures for the generation, detection, and or manipulation of infrared light. And the shorter version of that is that we try to do nanophotonics with micron scale photons. I'm going to talk a little bit about why that is so challenging. And of course, before I begin, I also want to acknowledge the fact that I don't get to go into lab anymore. And so it is my students who are doing all of this work that I'm presenting. So not just my current students and research associates, but also previous students in my group. I also want to sort of mention quickly that my group has a lot of different interests and we work across a range of different fields. So we have efforts on developing mid-infrared sources and integrated photonics, metamaterials. We'll talk a little bit about our bolometric detection and even working with optical phonons. I'm unfortunately not going to have time to talk about all of these different research efforts today, but if any of those seems interesting to you, I'm always happy to talk with you offline about these different efforts in my group. So what I am going to talk about today, I'm going to provide a sort of a quick outline of my talk. I first want to introduce you to this wavelength range that I largely work in. We've sort of expanded a little bit since I named the group, and so now it's just, we have the logos and I didn't want to change it. So we still call ourselves the Mid-IR Photonics Group, but we sort of have expanded that range a little bit. I'm going to talk about why we might want to work in this wavelength range, why it's important, and what the challenges are associated with working in the mid-infrared. And then sort of move on to talk about why we want to engineer materials and devices at these sort of temporal and spatial extremes, why that is important, and how we get there. And then I want to give you some examples of the sort of work that we're doing. I want to introduce you to the sort of field of infrared plasmonics. We're going to use this as a vehicle to talk about how we can engineer materials at these extreme scales. And I'll give a sort of brief introduction on sort of fundamentals, and then talk about our work looking at doped semiconductors, colloidal plasmonics, and nonlinear response. And then finally, some new work that we've been doing lately in a field that we've coined metaplasmonics. And then I'll end with some conclusions in future work. So why do we care about the mid-infrared? I don't want to spend too much time talking to this. When I started my career as a faculty, the mid-IR was something of a frontier. It's this wavelength range. Depending on what field you're in, one can quibble, but ostensibly sort of from 2 to 3 microns wavelength out to about, I don't know, let's say 20, 30 microns of that range. So why do we care about this particular wavelength range? Well, the first is that, and these are sort of glib responses, but everything absorbs in this wavelength range, right? So there's a whole host of molecules that have absorption spectra, and not just sort of broad absorption, but sort of these really clearly defined and unique lines. So in some sense, the mid-infrared is like a spectral fingerprint for different molecules. And oftentimes you will actually hear the mid-IR referred to as the spectral fingerprint or the molecular fingerprint region of the optical spectrum. Right, so everything absorbs, so that if you want to sense different molecules or materials, right, for say breath analysis or industrial process monitoring or environmental monitoring, right, you would want to have sources and detectors that can look at the wavelengths where those materials absorb light. And that absorption, because these are vibrational absorption of your molecules, is much stronger at these wavelengths than it is at shorter wavelengths or higher frequencies. Now, it turns out that physics tells us that if something absorbs at a certain frequency, that means it also emits at that frequency. So if it has an absorption resonance in the mid-infrared, then it actually has a thermal emission associated with that absorption resonance. So you might like, depending on, I'm dating myself here, but depending on your age, you might remember perhaps the first time you saw a thermal image was probably the Predator movie. So if you are being chased in a Central American jungle by some sort of alien, a good understanding of thermal emission can be very helpful. In more practical applications, I guess there's nothing more practical than that, I suppose, but like in more applications where you might encounter things perhaps sort of more day-to-day, you'll notice that like even graduate students have thermal signatures. I do not track my graduate students with thermal imaging components. We tag them with RFIDs, but if you, for instance, wanted to track a helicopter, right? Or even if you wanted to look at what portion of a microchip is using power and therefore dissipating power, a thermal image can actually give you an idea of where power dissipation is going on. So thermal imaging, there's sort of countermeasure applications, all work in this wavelength range. And then there's one other reason, which is sort of intrinsic to the actual wavelengths that we're talking about. These are long wavelengths compared to, for instance, visible light. And what that means is that these wavelengths don't scatter quite as well off of small particles in the atmosphere. And so there are these transmission bands that we typically call the mid-wave infrared and the long-wave infrared, where light can pass through the atmosphere without significant attenuation. And so there's a lot of interest in, for instance, free space optical communication in these wavelength ranges, right? For how do they describe it? For situations where you have low visibility, and what, of course, they mean is sort of in the battlefield is one of the places that they can go. But also that means that there's opportunities for instance, remote sensing, right? So if you can get light through the atmosphere, you might be able to look at molecules in the atmosphere. And so a lot of earth science applications, and in fact, some of our funding comes from these sorts of earth science applications in the mid-infrared. Now, what are the challenges of working in this wavelength range? Well, it turns out that the challenges are basically the exact same things I told you were the sort of the motivations for working in the mid-IR, right? So they are that everything emits in the mid-infrared, right? So if you're trying to make a sensitive measurement of mid-infrared signal, and you have this graduate student that's basically like a mid-infrared lantern, right? The thermal emission from your graduate student could overwhelm the signal that you're looking for. And this is, I mean, it's not just graduate students, obviously, it's anything that has a room temperature or sort of finite temperature will emit thermal emission, right? And so there's this significant background of thermal emission that you're dealing with, right? And IR detectors have to be able to differentiate between that background and that signal. And just like everything emits in the mid-infrared, everything absorbs in the mid-infrared, right? And this is actually a big deal. If you think about our entire telecom infrastructure, the internet, right? Our fiber optic communication, right? The reason why that operates at 1.55 is not because that's where we can make the best lasers and best detectors. I mean, it is now, but the reason it's the place where we can make those very good emitters and detectors is because of glass, right? This is where glass has the lowest absorption. And so we built an optoelectronic infrastructure around a material, right? A cheap and plentiful material, I might add. So this is, of course, glass in the visible, right? And if you take a thermal image of glass, same sort of picture, but you superimpose that thermal image over this person, you can see that the region that is glass is opaque. You can't see the person behind the glass when you take a thermal image, right? Glass is actually highly absorbing in the mid-IR. And so that's a big issue. And this is one of the main reasons why it's been such a challenge to develop optical infrastructure in the mid-infrared. We don't have a lot of cheap, good materials, right? And then that last advantage of the mid-IR, which is that the mid-IR wavelengths are long, also means that we have less scattering, right? That's good, but it also means it's much harder to get our mid-infrared light into sort of nanoscale volumes. Of course, what I'm going to be talking about today is how we can do mid-infrared optics and mid-infrared optoelectronics on the nanoscale. And that becomes hard when your wavelength is quite long. And then finally, sort of in its own category, as someone who has to run a research lab that predominantly works in the mid-infrared, is that all of these challenges associated with the mid-infrared conspire to make things really expensive to do in this wavelength range, right? So if, you know, these are somewhat dated prices, but if you wanted to buy a polarizer for the visible, for instance, these are Thor Labs prices, may cost you $100. In the mid-IR, it's $1,500, right? You want to buy a laser, right? We have cheap lasers integrated into everything. You probably have arrays of lasers in your iPhone, right? That probably cost, you know, less than $1 to put in there. And if you wanted to buy just individual standalone lasers from Thor Labs, you're talking 10, 30 bucks, something like that. You want to do the same thing in the mid-infrared, you're talking about thousands of dollars, right? And this adds up when you're running a research group. So, right. So what are the specific challenges associated sort of moving to these extreme length scales in the mid-IR, right? So developing nanoscale optoelectronics at any wavelength is hard. But in the mid-infrared, you have these extremely long wavelengths. And so what that means is you're trying to squish your light down into volumes that is sort of hundreds or maybe thousands of times smaller than the wavelength of your light, which means that you're fighting against the diffraction limit. The diffraction limit basically tells us that we can confine our light down to length scales on the order of the wavelength divided by 2, multiplied by the index of refraction there, n, right? So when you try to confine your light in sort of these small nanoscale volumes, what happens is that it basically just leaks out, right? And so therefore it becomes really, and that's not going to stop someone who's trying to get funding from arguing it, but it's very difficult to argue that the mid-infrared is a particularly good fit for purely nanophotonic reasons, right? So what I'm saying here is that if you want to make optical interconnects, if you want to take light from one place to another, say on a chip, or you want to do quantum communication or computation, you want to do nanosensing, right? You want nano emitters and nano detectors and nano waveguides, right? But if you do not have a specific reason to operate in the mid-infrared, right? If your application is essentially wavelength agnostic, you're just trying to get a signal from point A to point B, and you want to do that using up as little volume as possible, there's really no reason to go to these wavelength ranges. There's really none, right? I know that's not the best pitch for the remainder of my talk, but there actually, of course, are very few wavelength agnostic reasons to do anything in optics. And so why would you perhaps want to go to these sort of length scales in mid-IR, right? Well, the first is entirely pragmatic, right? If you think about advances in microelectronics, for instance, right? Moore's law, with we're condensing more and more transistors onto a single wafer, right? There's just an advantage in terms of cost there, right? You can just make more of them in the same area, right? So reducing dimensions, of course, reduces costs, and it opens perhaps up new applications. Right now, we can just put microchips in everything. We can put lasers in everything. We can put detectors in everything. Think about the phone on your iPhone, or the camera on your iPhone, which is sort of better than these big bulky cameras that we could buy 20 years ago, and now they're sort of the size of a quarter. Right, so being able to reduce dimensions gives us some real benefits, and oftentimes it actually improves at least some performance metrics of the devices that you're working with, right? But there's also a sort of fundamental reason why we might want to go down to these sort of extreme length scale, right? Because it essentially allows us to see at a scale that was sort of previously unimaginable. And I'm showing work here from various groups looking at surface waves and at these sort of long wavelengths, but at the nano length scales. Right? So fundamentally, there's a reason why we want to go to these extremes. And the same thing goes for time scale, right? So if you can squeeze more things into an area, then you can make more per unit area. And of course, and if you can squeeze more information into smaller time scales, then you can send more information in a given time frame, right? So it allows us to do things faster, right? You can think about the dramatic advances in communications over the last 5-10 years. A lot of that is coming from our ability to sort of reduce the time scale associated with operations in sort of optoelectronic devices, right? And again, it improves some performance metrics. And then there's this sort of fundamental reason as well, which is that if we can get down to these sort of extreme timescales, then we can actually image things. We can think about sort of cameras operating on the sort of at-a-second timescale, right? Where we can measure things at, again, timescales that were sort of previously unimaginable, right? And if you're really good, then you might win a Nobel Prize for doing it. So there's good reasons to go to extremes. So then in the mid-infrared, how do we do this? Well, one of the reasons why I really like working in this wavelength range is because we have access to all sorts of great light matter interactions. And ultimately, if you want to design devices and structures that operate at these extreme scales, whether it's temporal or spatial, right, you need mechanisms to interact light and matter. So that's basically it boils down to, right? So in the mid-infrared, we have materials that behave effectively like perfect electrical conductors, right? We have plasmonic materials. I'm going to spend some time talking to you about those today. We have, of course, dielectric materials, but they're not as plentiful as they might be at shorter wavelengths, but we certainly have some dielectric materials. We can leverage optical transitions in semiconductor materials to detect or generate light. We can even harness vibrational modes in our crystals, right? These phonons that interact very strongly with light. And we even have nonlinear response in many of these materials. And the reason why the mid-infrared is such an exciting place for me to work is not simply because we have all of these different light matter interactions. It's because we can actually engineer so many of them. We can control them. We can design materials, right, to enhance nonlinear response. So we can design materials to emit light at a certain wavelength. We can control optical transitions at these wavelengths, right? So we don't only have access to, but we can engineer all these things. And so this is a really powerful toolbox for going to extreme temporal and spatial scales in the mid-infrared. Okay, so I want to move on to talk about some sort of fundamentals of highly confined modes in the mid-IR. And I'm going to focus, like I said, I'm going to use this idea of plasmonics as sort of a vehicle for this discussion, and to talk about how we can squeeze light down into the nanoscale. So one way to beat this diffraction limit, right? This diffraction limit that says that if you're working with a traditional dielectric material, you can really only confine your light down to length scales of lambda over 2n, right? And that's because your light is light. It's sort of purely photonic. But one way around this is to couple your light to a material excitation, right? So this is known as a polariton, right? So it's a hybrid excitation of an electromagnetic wave coupled to some collective excitation in your material. And there's different collective excitations that you can couple to, right? There are phonons, the lattice vibrations. There are excitons, right? These are sort of coupled electron hole pairs. And there are plasmons in view. But plasmon is essentially an excitation of charge. So these are charges that are sloshing around. Charge is much heavier than photons. And so basically this field of plasmonics is the field of optical modes that are supported at the interface between what we call an optical metal and a dielectric. When I say an optical metal, what I'm talking about is a material whose permittivity is negative, right? This is the way that we're going to define metals in the optical regime. So what you have is for instance, in this case, this is a surface plasmon polariton, right? This is a polariton means it's this hybrid excitation. Surface means that it's at the surface of our optical metal. And so this is a mode that propagates along the surface of the optical metal, right? Consisting of a charge oscillation or a plasma in your metal, and then this electromagnetic wave that is tied to that charge excitation on its surface, right? This is a dispersion relation for a surface plasmon. It gives the momentum of this mode as a function of frequency and the dielectric of your material, right? And by the way, you can see this is the permittivity of your dielectric, this is the permittivity of your metal. When the permittivity of your metal and the permittivity of your dielectric are equal but of opposite sign, then this denominator goes to 0, right? And your wave vector effectively goes to infinity. So what does that mean? Well, the wave vector is essentially the inverse of your wavelength. So now the wavelength of your surface plasmon polariton has gone down to 0. Now, of course, nothing ever works the way it should. Like there's losses, and so we can't get down to 0 wavelength. But we can dramatically reduce the wavelength of this mode, and therefore we can start thinking about confining this light into sort of sub-wavelength dimensions. We can also excite what's called a localized surface plasmon. This is a localized mode that is tied to some sort of 3D structure. In the simplest case, it might just be a sphere floating in vacuum. And again, you can see that in the denominator for the polarizability, or essentially electric field tied to the outside of the sphere, we have essentially a term where we get very, very strong electric field enhancement when the permittivity of your metal is equal and opposite-ish of your dielectric. This X is just some scaling factor depending on the geometry of your structure. But there are, as I mentioned already, fundamental trade-offs. So this is from a paper all the way back in the 70s. And by the way, people have been looking at surface modes on metals for, I think, probably over 100 years at this point, right? It got really, really popular in the early 2000s when sort of put together some advances in computational techniques and fabrication and measurement. But people have been looking at surface waves on metals forever. And they point out that as k goes to infinity, in other words, as your momentum gets incredibly large, your wavelength gets incredibly small, right? Then what happens is the fraction of the energy in this wave stored in the electromagnetic wave becomes progressively smaller. So if we think about this, the reason we can condense these waves down to sub-wavelength scale is because the matter waves, right, are much sort of smaller, right? They're what gives us the size compression. And as we transfer more and more energy into those matter waves, right, then what happens is, yes, our k gets larger, our wavelength gets smaller, but now we dissipate that energy by shaking charge around, right? And so what happens is basically, at some point, right, you're just limited. You just, losses prevent you from confining your wavelength down to these sort of really small scales, right? So in other words, what this means is you can achieve very, very strong mode confinement in a polaritonic medium, right? But at this extreme, your energy is stored in the media's collective excitation. And this leads to loss, right? Alternatively, right, you can operate in the regime where your mode is more electromagnetic. which case you'll have lower losses, but you're effectively diffraction limited, right? So you're weakly confined. And you can see that this is the dispersion of a surface plasmon mode. You can see that as it bends, this is the light line, so this would be light propagating the material. As your mode bends away from the light line, as K gets much larger, right, your loss, the blue line, goes through the roof, right? So it's this trade-off. There's always these trade-offs, right? Now, I'm not the only person to, I mean, obviously I'm quoting from 50 years ago. My friend Jacob Kurgan has noted this on numerous rather snarky papers. This one is one of his less snarky papers, but he basically points out that plasmonic nanostructures can really only enhance the efficiency of originally very efficient processes. In other words, if you're going to use plasmonics to make efficient emitters or to sort of strongly confine light, and you already have a good emitter, you're going to make it worse, right? You might make it smaller, but you're going to make it worse. Well, the lucky thing is in the mid-infrared, if there's like one thing we have, it's inefficient processes. Like that is, I mean, I'm not an expert in much, but like I'm very expert in inefficient processes in the mid-infrared. So here we actually have a wavelength range where we might be able to gain some real benefit, even though we have these losses associated with our strong confinement, still might make these emitters or detectors better than they would otherwise be, right? So the question becomes not like, does this, are we willing to sacrifice poor performance for being smaller? The question is like, can we actually go smaller and get better performance? And that's one of the things that I want to show you today. Now, can we do this? So I guess there's a question here. So, can we essentially make this trade-off with traditional metals? So for shorter wavelengths, typically, right, when people do plasmonic work, they use gold or silver. In the mid-infrared, right, if we wanted to sort of leverage these plasmonic modes, could we do that with gold or silver? What I'm showing here is the permittivity of silver. If you look, right, in the mid-infrared, you'll notice that the permittivity here is quite large and negative, on the order of -100 to -1,000. And remember, all of the good stuff for plasmonics happens when the permittivity of your metal is approximately the same as the permittivity of your surrounding dielectric, but flipped in sign. So we don't have dielectrics in the mid-IR that go to -1,000. So the region where these noble metals are plasmonic is actually here in the visible, right? Where you sort of have permittivities that are on the order of sort of the dielectric that you could expect from an electronic material, right? And then there's sort of this kind of neat physics range where your permittivity actually crosses to 0. There's some interesting stuff there. So what this means is that even if we wanted to like leverage these trade-offs with traditional metals in the mid-infrared, we couldn't do that, right? And there's some actual real implications, right, of using noble metals. So if I look at, for instance, the penetration depth, in other words, how tightly I can confine this mode, and the propagation length, what you'll see is that as I move to these long wavelengths, my penetration depth gets very large. In other words, my mode extends for 10 wavelengths, for instance, beyond the metal. So that is not sub-wavelength confinement, obviously. That's 10 times the wavelengths. This is not really a plasmonic mode in any sort of sense of the word. This is just a surface wave on a metal, right? Now, the advantage is, of course, that it propagates for a very long distance, but that's because it's loosely bound. It's not really exciting the charges in your metal. This is not really plasmonics, right? And again, if you're looking for the resonance associated with the localized mode, you can't hit it because your metal permittivity is too large today. So if we look at how to describe the optical responsive metal, the way that we typically do this is with the Drude model, right? So you can do a Drude model with sort of basic sort of treating electrons using Newton's laws, right? And it's a really nice derivation sort of give to like a junior level student in E&M. And you can actually calculate what the permittivity is given a scattering rate as a function of frequency, right? And it depends on this plasma frequency. The plasma frequency is the frequency at which your material's permittivity goes through 0. And if you do this for a typical metal, right, what you'll see is that in the mid-infrared, this is quite large and negative. And the reason for that is that your plasma frequency is too high. In other words, there are too many electrons. N is the number of electrons. Too many charges, right? In a metal like gold or silver, you 10 to the 22nd, 10 to the 23rd free electrons sloshing around, right? And it pushes the plasma wavelength to the visible or UV. So in order to do this sort of work in the mid-IR, we need to be able to make our own designer metals. So what I'm going to talk to you about is sort of three approaches that my group takes to doing this. Right? So the first is using epitaxial semiconductor plasmonics. I usually spend a long time talking about this. I'm going to shave this portion of the talk down. I'm going to briefly talk about my work in this area. I'm going to talk about a collaboration with Delia Milliron's group at UT Austin, where we're looking at colloidal semiconductor plasmonics. And then I'm going to end with some new work from my group that I'm sort of really excited about that we call metaplasmonics. Okay. So let's talk about dope semiconductors. So we have too many electrons. This is why we can't do plasmonics in the mid-infrared. But what if we had a material system where we could start with a dielectric and then we could put in the free carriers that we wanted? Well, we have those materials. They're called semiconductors. And we have a way of putting in the free carriers. It's called doping. So we grow our semiconductor materials by molecular beam epitaxy. This is a picture of a half wafer in our chamber, right? And we basically have these ovens. We heat the ovens up, we open them up, and the elements there's a molecular beam that carries them to the surface, and they arrange themselves atomic layer by atomic layer. So we can grow these materials, and then we can dope them with, in this case, silicon, provides free carriers into the system, right? And when we do that, for instance, in this case on a layer of indium arsenide, what you see is rather distinct. You see these oscillations at shorter wavelengths. So this is just Fabry-Perot modes of light bouncing around in this dielectric material. And then you see the sort of sharp turn on to high reflectivity. This is where your material becomes a optical metal. In fact, right around here would be the plasma wavelength. This is one of the very, very first samples that we grew. And if you model this simple sort of three-layer stack with a transmission matrix method, and we use the Drude model to describe the indium arsenide, it actually gives us a pretty darn good fit. So we can basically make our own metals in our epitaxial system where we have sort of atomic level control of thicknesses, and we can control to our heart's desire essentially the amount of free carriers that we put into these materials. And what you see is that we can essentially, this is the same basic material, indium arsenide in this case, and we can tune the plasma wavelength, the region where our permittivity crosses zero, across the mid-infrared, right? And now what this does is it gives us a material system, right, where we can go from, for instance, a low index material to an epsilon near zero material, all the way to a plasmonic material, right? And we can do that as a function of wavelength, or we can control the doping, and we can shift that as well. And we have work in sort of all of these different areas, right? So we can dope these materials in such a way that the refractive index is decreased, but it's not an optical metal. And then we can, for instance, make DBRs out of these, like mirrors, reflecting mirrors. We can actually look at the region where the permittivity is zero. We showed that we can actually funnel light through these sort of really, really sub-wavelength apertures using epsilon near zero materials. This is an old work from when I was back at UMass. We can even make little plasmonic nano antennas out of these, right? So these are nano antennas that operate at 10, 11 micron wavelengths, but they're only a couple hundred nanometers in dimensions, right? So we can leverage all these different sort of regimes of operation of our dope semiconductors. We can even stack our dope semiconductors with undoped semiconductors to make these hyperbolic metamaterial structures that actually bend light with a negative index of refraction. We can make negative index waveguides, and we can even take these metamaterials and we can fabricate them into these funnels, and we can effectively funnel our light down to these, nanoscale tips, 10 micron light, and we can sort of funnel it through these metamaterial funnels into these structures. But I want to talk about how we can leverage these sort of plasmonic materials for optoelectronic applications. So we have control, like I said, one of the reasons why the mid-IR is so fun to work in is that we have a lot of control over the optical transitions at these wavelengths. And we can design, these are known as type 2 superlattices. So these are alternating layers of different semiconductors that basically create a superlattice, and we can engineer these, right, to essentially give us mini bands, and we can control the spacing between the mini bands so that we get essentially an effective valence band, an effective conduction band, and we can control where that transition is. And then we can, because these are heterostructures, we can integrate them into device architectures. So in this case, I'm sure this is just a PIN diode, but we can also make these barrier devices, which are used for detectors. So we have a lot of control over these materials, right? So if you think about what we need to be able to do sort of an optoelectronic device leveraging plasmonic materials, we need to be able to control the permittivity. We need to be able to integrate the sort of optical materials with quantum engineered active regions. That's what I just showed you here in electronic device architectures, which is what I just showed you here, right? And we really need to be able to do this in the same material system. And I didn't mention it, but it is in fact the case that everything I showed you here is using the so-called 6.1 family of semiconductors. So we can make emitters and absorbers and plasmonic material and low-index material. We can do this all in the same material system, and we can do this epitaxically. So we can do this sort of the highest quality semiconductor crystals that you can get. So we have all these capabilities now, right? So how do we employ them? Well, I told you at the beginning of the talk that going nano sometimes gives you significantly improved the device performance metrics. And that is in fact the case with detectors. So it turns out that in a detector, what you would ideally want to be able to do is absorb as much light as possible in a very small region. And the reason for that is because noise in a detector, which is sort of half the performance metric of a detector, essentially a detector, you measure the performance of the detector by the signal you can get divided by the noise, right? And the noise goes as the square root of dark current. And the bigger your detector, the more dark current you have. Now the problem is, as I said before, what we have in the mid-infrared are very inefficient processes, which means that we don't have very good absorbers, which means that our absorption is weak. So if we want to absorb a lot of the light that's incident on a detector, we have to grow a thick detector. If we grow a thick detector, then we have a lot of noise, right? And so we're improving one metric at the expense of another. But now we have this way of making materials that we know can confine light to very, very small dimensions. And we can integrate them with optoelectronic materials and device architectures. So maybe there's a way that we don't have to trade off absorption for noise. Maybe there's a way we can make a very thin detector, right? But still absorb just as many photons as before. And so we've done a number of different sort of designs. I'm going to talk about one design specifically. This is a plasmonic detector we designed that basically has a layer of this optical metal that we grow first. And then on top of that, we grow our detector structure. We grow a very, very thin detector structure. We put a grating on it. See that sort of here, right? That couples light into these plasmonic modes, these really tightly bound modes at the interface between our metal and our optoelectronic device architecture. And what you see is you see an enhancement of your absorption at 10 micron light. This is a detector that's only about 330 nanometers thick, and it's absorbing light at 10 microns. Typically, a detector that's operating at 10 microns would be on the order of 5 to 10 microns thick, right? So we've reduced the thickness of this detector by over an order of magnitude, and therefore our noise will go down as well. And in fact, you can see this is the sort of the state of the art, or it was the state of the art for Merck-Cattell detectors, which are the standard for mid-infrared detectors. And you can see our dark current, right, is well below that. And in fact, what that means is that we can operate these detectors at higher temperature. So this is our first generation of detectors, and this is sort of what's commercially available. This is our second generation of detectors operating at 230 K, with access with the thermoelectric cooler. This is sort of what you can buy on right? So the ability to be able to engineer these optical modes and integrate optoelectronic device architectures with them, right, has real, actual, practical advantages in terms of optoelectronic device performance. I said I'd be really quick. I actually have no idea what time is it? Oh, how am I at time?
I think I got it.
I got time. Okay. All right, I want to talk about a slightly different material system. So what if, like, let's take a step back and say, what if we just want to absorb light with our plasmonic material? We don't want to convert that, let's say, into an electrical signal. We just want to turn it into heat, whatever. We don't care where it goes. We just want to absorb that light. Now, of course, the smaller the volume of your absorber, right, the more energy per volume you'll be depositing in that absorber, and whatever you're using that for, so the more concentrated that energy is going to be, right? And say you want to measure a temperature change, you want to convert your incident radiation into a temperature change, then presumably you would want to absorb, right, that light in the smallest volume possible, right? Now, it turns out that for most optoelectronic applications, loss is actually something that you're trying to avoid. You don't want your optical photons, turning into heat, right? But there's a huge sort of field of literature, and you can find this if you do a simple, Google Scholar search for it, on perfect absorption. Now, I have a sort of cynical view as to why that is the case, because if there's one thing it's really easy to do when you're trying to make a new material, it's get it to absorb light. It's actually usually what you're trying to avoid. Like loss is what you're trying to avoid. But you make a new material, it absorbs a lot of light. It's not what you wanted, but you can call it a perfect absorber and you can get a paper out of it, right? And it's approximately done 2,000 times a year now. But, right, that's not to say that there aren't applications. In fact, you can go back to 1881. So again, sort of cutting edge science here today, to the sort of introduction of this thing called bolometers, the first infrared detector. And basically, it's a wheatstone bridge with an IR absorbing material, lampblack soot on one of the arms, right? And essentially, when light hits that, it heats it up, it changes the sort of balance of your bridge. And this could actually detect a cow, and when it detect the thermal emission from a cow at a quarter of a mile in 1881, right? This is actually really impressive. And by the way, again, so it goes back to the idea that the things that we do have practical applications like cow detection, and also fundamental applications, because what this actually, the development of this device is one of the reasons that allowed us to understand that light and heat were actually intrinsically linked. They called heat at this they called it actinism, right? But in fact, what that meant is that this allowed us to see that there's this link between thermal energy and optical energy. So, the importance of the development of new tools is not just that they have practical cow sensing applications, but also, right, that we learn new science. They sort of they open the door to sort of new understandings for us, right? Now, the transduction of light to heat has current day applications, right? Little nanoparticles that can absorb light and heat up and burn off tumors, for instance. Or even to make light sources. Again, I told you that if something absorbs in the mid-infrared, it means it also emits in the mid-infrared, right? So we can make emitters in this wavelength range by heating up things that have engineered absorption resonances. Now, we started thinking about what is the maximal light absorption that you could get in the minimal possible volume, right? Why would we want that? Well, the more you concentrate the light, the more sort of interesting effects you can get. So for instance, nonlinear response, right? Purcell enhancement, right? Really efficient absorbers. So start thinking about what is the ultimate thickness limit for which one can achieve perfect absorption. You can absorb all of your light, right? So we didn't find sort of a material agnostic analytical framework for doing this. I should note that a lot of this work, all of this work was done by my spectacular research associate, Darko Sakatic. You'll see his name on a lot of the papers coming up here. I'm going to show you. So it turns out that people have been looking at how to absorb light efficiently in thin layers for many years, not surprisingly going back to sort of radar times, right, when people are really pushing on radar. There's this Waltersdorf thickness where Waltersdorf calculated exactly how thick a layer of metal had to be to absorb the maximal amount of radiation if it was just floating in space. It turns out the most you can absorb is 50%. And so Jarko started thinking about, well, what happens if we have a thin film, but it has an absorption resonance in it? And then moreover, what happens not just if we consider that thin film, but we consider it in a sort of very simple open cavity system where we have a perfect electrical conductor and then some space related, right? And so it turns out that you can calculate what we call a resonant Waltersdorf thickness that shows you how thick or thin that material needs to be to absorb all of the light incident on it, whether it's freestanding or whether it's mirror back. And one of the things you notice is that it actually doesn't depend on the real part of the permittivity. It only depends on the imaginary part of the permittivity, right? And so if you have a material with a strong absorption resonance, so let's say like a phononic material, like any one of these polar semiconductors, which have very, very strong epsilon double prime at these sort of long wavelengths, you can make a thin film that absorbs all of the incident light that is only, for instance, in some cases, nanometers thick. Nanometers thick, right? So this is, on the order of 10 microns, and you can absorb every single photon in a thickness of 6.5 nanometers, right? And so this sort of allows us to develop a framework for making these sort of ultra thin film absorbers. And then we thought, well, okay, well, we should show that we can do this. And it turns out it's very hard to do this. It's really hard to grow materials this thin. And I'll talk about one way that we can get around that. But we were working with Delia Milliron's group in chemical engineering, and she has, interestingly enough, these plasmonic nanocrystals. Well, these are tin-doped indium oxide, and she can control the diameter and the doping, so the number of free carriers in them, and they behave like these localized surface plasmon resonators. And it turns out when you deposit them in a monolayer, what you effectively get is like a collective excitation of these surface plasmons. And their absorption looks pretty similar. This is epsilon double prime. It looks very similar to sort of what we need to get this perfect absorption in thin layers. So we thought, well, okay, if we put these layers of nanocrystals on our sort of open cavity structure, we should be able to actually get perfect absorption. And that's in fact what we see here in a single monolayer of this material. And this is pretty angle insensitive. We can control sort of the width of our absorption by controlling the number of layers. We can go from undercoupled to overcoupled to critically coupled. We can tune across wavelength by controlling the thickness of the cavity, by controlling the doping of these nanocrystals, right? And so we can basically build these perfect absorbers across the mid-infrared. Why do we care? Well, one reason we might care is because when you concentrate that much energy into a very small volume, interesting things start to happen. In fact, for these materials, what we were sort of thinking we would see is we have this really strong electric field confinement, incredibly strong interaction with our free electrons. And when that happens, they get kicked up to these higher energies. They behave differently. Right? So they slosh around in a different way, which means the permittivity changes, which means you get out of resonance and you're no longer perfectly absorbing. So the idea was, if we apply a pulse of laser light, can we go from this sort of zero reflection state to a reflection state where we have high reflection, right? And the answer is, in fact, where is the answer? The answer is coming up here. Here we go. So if we just put these nanocrystals on a silicon substrate, we see maybe a 2% change in reflectivity. But when we put it on our cavity structure, we basically go from zero reflectivity up to 40% reflectivity. It's an enormous change in reflectivity. And it says some real implications for sort of optical switching and mode locked lasers, right? But what's even cooler about this is that when we look at, so these are a bunch of different samples at different wavelengths under sort of femtosecond pulse excitation. But this is a pump probe measurement that actually measures the temporal response of this reflectivity change. And what you see is that you look at the time scale associated with that change, it's on the order of hundreds of femtoseconds. So sub-picosecond switching. In fact, this is the limit of our measurement system. It might be faster, we don't know. Right? So this opens the door to being able to do sort of high frequency terahertz frequency switching in the mid-IR using these sort of really cheap large area materials. And so there's a number of applications that we're sort of pushing on for leveraging these materials. Okay, the last thing I want to talk This will be quick. So up until this point, we've achieved plasmonic response by taking a dielectric and adding charges to it. So whether that was my doped semiconductors that I talked to you about, or these nanocrystals that Delia dopes with tin to give us our free carriers. We've taken a dielectric and we've added charges to it. We put enough charges in there that we get this plasma oscillation that can couple to our optical waves. But what if we went the opposite direction? What if there was a way to take charges away from metal? Well, that's actually pretty hard to do, but we got some clues from both some of the previous work I was talking about and sort of one of the recent hot fields in plasmonics, which is plasmonics in atomically thin crystalline silver film. So it turns out that when you start looking at plasmon modes in really, really thin films, you can get these bound modes that actually show pretty strong confinement in the mid-infrared. So you have to reduce the thickness of your metal immensely to the point where you can treat it essentially like a 2D conductivity. And then you can support a mode that essentially exists on both sides of this film. Now, the problem here, and by the way, if you do this, what you'll see is essentially you'll see your dispersion curve bend away from the light line, which is sort of the characteristic that we showed associated with surface plasmons. Now, the reason why this is quite challenging is because, first of all, it's really hard to make nanometer thickness metal films. If you've ever deposited metal in a thermal evaporator or a sputterer, you know that there's a percolation thickness. You have to get to a certain thickness before you can even sort of hope that it's planar. So it's very good. There are ways to do it. It's just really expensive. The other is sort of intrinsic and fundamental and something you can't get away from. And that's the fact that the minute you go down to a thickness of your metal that is below the mean free path of your electrons start bouncing off the edges of the metal. This is called Landau damping. And it effectively adds a scattering term to your electron motion, which scattering is loss, right? And so you're intrinsically limited by the dimensions of your metal. And the minute you start being able to get this strong confinement at IR frequencies, your loss goes through the roof, right? So we had been working on these sort of perforated metal films because we had been using that paradigm for perfect absorption. We were trying to do it with metal films, and we realized that to get perfect absorption using a metal film, we had to go to thicknesses that we couldn't grow. So we thought, well, what if we just poked holes in our metal, right? And we effectively reduced the permittivity because these holes are so sub-wavelength that light doesn't really see the periodicity. And we can effectively reduce the permittivity and reduce the loss, and we can essentially impedance match these to incident light and get perfect absorption. And so we had a nice paper that, again, led by Jarko, showing that worked. But then we started thinking, well, we might be able to actually approximate atomically thin metal films doing this. So instead of having an atomically thin metal, we can just take our metal and we can perforate it in such a way that we reduce, like we just take away all of those free carriers. Now, this only works if you can do this on a length scale that's smaller than the wavelength of your light. Because otherwise you'll get diffraction and all sorts of other effects. So this is what your dispersion looks like when you change the gold thickness down to 2 nanometers. And this is what happens when you essentially reduce the fill factor of your metal. Right? And if I didn't have the legends here, you wouldn't be able to tell the difference. From the point of view of light, it can't tell whether you've made it thin or you've just chopped out chunks of a thicker layer. So what actually this does is we can engineer this in such a way that every dimension is larger than the Landau damping, right? It allows us to even go to longer wavelengths with what we are calling the sort of metaplasmonics approach, and we don't get hit with those loss penalties, right? And so we looked at, for instance, could we make resonators out of these nanoplasmonic films? And you can see, in fact, that if you look at the dispersion, experimental dispersion of these resonators, they behave a lot like a 3 nanometer thick metal film, except for our film is 30 nanometers thick and it's perforated, right? And in fact, if you look at our experiment and our simulation, you see that we get these sort of nice nano antenna responses. These are nano ribbons. You can look at our mode confinement. It's on the order of lambda over 30, lambda over 40. We think we can hit lambda over 100 or lambda over 150. So we can take 5-10 micron light and we can condense it down to the nanoscale. Now we can start thinking about how we can interact that light with sort of quantum systems and single sort of quantum emitters and these sorts of things in infrared. Right? We can stretch these, and that enables essentially tuning of our resonance, right? And so we feel sort of our simulations suggest that, you know, for these sort of metaplasmonic films on gallium arsenide, we can hit confinement factors of 100. So our wavelength can actually go to 100 with a free space wavelength. We have simulations that suggest that we can actually go a couple times higher if we use silver. And we can extend the operation. So this is sort of the work that's been done using these atomically thin films, but our metaplasmonic films, we can sort of bring those out all the way to the long way to infrared because we're not fighting against that Landau damping effect. Now, there's one other thing that's really cool. This is my last slide. And this is the fact that we're effectively, what we're doing is we're effectively diluting the permittivity of our metal by perforating it. And of course, there is some geometry because it's not just a matter of modulating the conductivity of your metal film. You're also, there's a reactance there that you're messing. And it turns out that depending on your dilution in different directions, you can actually engineer these metaplasmonic films to have different permittivities in different directions. So this is, for instance, the permittivity in the X direction, might be the permittivity in the Y direction. And this is, of course, what a flat metal film looks like. So this is, I should say, this is the dispersion of your surface plasma mode in X and Y. This would be the dispersion in just a flat metal film. Now, what that means is that you actually have an anisotropic metal, right? Metal, of course, is isotropic. You deposit a metal, it doesn't, like, there's no way to tell X and Y. But here we can engineer the optical behavior of our metal in the X and Y direction. And what that means is that we can actually engineer these propagating modes so that they have, for instance, this is what, if we put a dipole above this surface and we look at the field, right, we can measure the field generated by a dipole. And you can see that this is what we call an elliptical dispersion, right? The waves have different k vectors in the different directions that are generated by this dipole. If you take the Fourier transform of this mode profile, what you see is an isofrequency curve in k space. So this is essentially this is all the same frequency, right? And you can see that for that frequency, you have a larger, for instance, kx than you do ky, right? So this is essentially an anisotropic medium, but right, you can actually look at this film in regimes, for instance, where you cannot propagate, for instance, in X, but you have a dispersion in Y, and that gives you something that looks like this. This is the mode profile of this is the mode that's generated by a dipole sitting right above one of these films in a region where the film behaves like a hyperbolic medium, right? And the mode, right, you can see it's highly directional, and the wavefronts have this sort of hyperbolic shape, and that, in fact, when you transform that, what you see is, this is just the dipole signal, but what you see is actually hyperbolic dispersion, right? And that actually can give you like a massive optical density of states, all sorts of interesting things. In fact, I think the physics is even richer than that. You can go from sort of anisotropic behavior to these things called Diakonov plasmons. You can even get this crazy canalization effect, where essentially your hyperbolic dispersion flattens out and you get the sort of single directional propagation to hyperbolic behavior, all in the same film as you sort of go through the different regimes of operation of this film. So it's essentially an engineered plasmonic material, but it's one where not only can we control the plasmonic response, but we can control the direction of that plasmonic response. So that was the last thing I wanted to talk about. I'll end by saying the mid-infrared, I think, offers a sort of unique spectral range to engineer optical properties of materials. Right, you can engineer the dielectric, you can engineer permittivity. I showed you a bunch of different ways of doing that, either by changing the material response or by patterning the material, right? And we've shown sort of strong confinement of optical light, either by carrier concentration in semiconductor and noble metal films. We've shown that we can reduce the active volume of our devices and structures, and we can actually do so, but actually realize gains in our device performance. And the idea to sort of take sort of the way that my group works is we sort of start with what we think is interesting physics, and then we try to take that and move it towards devices and structures that have applications, all the while starting to look at some different interesting physics and eventually take that. So that's sort of, I've tried to show you a couple of things at different stages of development, whether it's the detector work that's sort of we're making actual devices that compete with state of the art, or whether it's some of the new stuff like the metaplasmonic films where we're still trying to figure out exactly what we can do with them. So with that, I will end, and of course, if you have any questions, I'd be happy to try to answer them. Yes.
Hi, thanks for the talk. That was really great. My question was on that last topic you were talking about, and I was wondering if you had any ideas for potential applications for something like this. Just, I know you said right there at the end that you're still trying to figure out.
Yeah. No, that's a good question. So the short answer is yes. This gives us like extremely strong confinement of our optical modes. And typically, you know, I was saying at the beginning of my talk, when you, for instance, a typical mid-IR detector is 8 microns thick, right? Or yeah, 8 microns thick to absorb long wave infrared light, get like a reasonable signal. And of course that you pay huge penalties for that, like in terms of growth time, in terms of like the challenges associated with growing a heterostructured material that thick. Here you have an optical resonator that is relatively low loss that confines your mode down to 10 micron light, confines it down into a range of 30, 40 nanometers. So then the challenge becomes, well, how do you get your optoelectronic device into a length scale that small? Because, for instance, your superlattice absorbers, those require like many periods to get that miniband effect. So we started thinking about new types of device architectures that we can put into sort of 10, 20, 30 nanometer like spaces, right? So those could be sort of quantum dot, quantum well type structures where we couple an optical transition to this sort of very strong optical mode. Or it could be sort of new ways of generating optical transitions in semiconductor materials that sort of typically wouldn't be used because they're not particularly efficient. But if you can put them in the near field of a plasmonic mode, then you might actually be able to make them function. So yes, we're thinking about, right now, we're largely thinking about emitters. We want to generate light in our material and couple it out to free space. But there may also be applications in sort of detectors or even modulators, right? Anytime that you can squeeze your light down to very small volumes, then you don't need to change as much material to get a response, right? So, yes.
Hi, thank you for that talk. I wanted to know, since you mentioned that the purpose of using the mid-IR region is to interact with the nanoscale, I was wondering, do you have any idea by using the nano antennas and the other materials that you mentioned engineering earlier on, what do you anticipate the temporal and spatial limits to actually be once you're able to incorporate those materials?
Yeah. Well, so for the colloidal work that we know that the temporal response is on the order of hundreds of femtoseconds or faster. And so that has some real applications, right? You can you think about like a light switch that you can turn on and off in 100 femtoseconds, right? You can use that to probe sort of temporal probing of processes, for instance, in maybe in a cell or something like that, or molecular dynamics or something on the sort of femtosecond time scale. So those we have a reasonably good idea of sort of the time scale associated with that. Those plasmonic modes, those should be pretty fast. It's the semiconductors that are going to be a little bit slow there. Typical semiconductors operate on sort of time scales, like the mid-IR absorbers tend to it takes like a microsecond for those carriers to sort of fall back down. So it's really hard to make an efficient or a high speed. I didn't show the work, and I don't know if I have it in my supplemental slides, but we have done work looking at the temporal response to some of the doped semiconductor materials. No, I don't know. I'll find it. Yeah, so it turns out actually, and this is it's so thank you for asking this question because it gives me the opportunity to talk a little bit about this. It turns out that if you can make your detectors very thin, you can actually pull the carriers out much faster. They don't have to travel through 8 microns of material to be collected. So we've shown that in our long wave infrared detectors, we can achieve time resolution on the order of like a couple hundred picoseconds, which is really, really fast for a mid-IR detector. It's much faster than you can sort of buy off the shelf. So, you know, it really depends on the device architecture you're working with, what sort of temporal length scales you're going to achieve. But for a you know optoelectronic device, we're looking at sub-nanosecond, and for these sort of all optical structures, we're looking at sub-picosecond. Yeah. Yes.
Thank you for the talk. I'm doing research on plasmonics, so it's really interesting,
Oh.
your work. I'm just wondering, you mentioned semiconductor plasmonics. Is there any study based on the, I don't know, how these plasmonics work after a certain time? Let's say after 6 months or 1 year, is the same performance after that sort of time?
So for the epitaxial semiconductors, there's no degradation. Those materials are pretty robust. You know, epitaxial materials are, I mean, maybe if you sent them to space, like people are still looking at, you know, the radiation hardness of 3.5s and stuff. That's depends on a lot of different factors that I'm not an expert on. The nanospheres or the like nanocrystals, I'm not as sure about those. So that's my collaborator Delia Milliron. I would imagine that those are probably more chemically reactive, and they certainly have more surface area to volume ratio than a epitaxial semiconductor. So those might degrade over time. We have seen degradation, but we've also been blasting it with like femtosecond pulses of lasers. So my guess is that that's probably more like a heating effect than it is a chemical effect. Yeah. Yes.
The detector that you put the performance of at 230.
Yep.
Was curious if there's more work being done to increase the temperature there, or what
Yes.
some of the challenges are.
Yeah, I mean, the challenges are that dark current goes exponentially with temperature, and everything we engineer seems to be linear. And a lot of times it's linear in the wrong direction. So that's the big challenge, is that you're trying to make linear increments on an effect that changes exponentially with temperature. So yes, we have a program from NASA. We have a program from Army Research Office to try to make sort of high temperature detectors. Yeah, we have a number of ideas. We have a number of things that we're working on, but like I said, they're all sort of linear, and this is the problem. And I don't know. I mean, temperature is one of those sort of intrinsic innate effects that's really, really hard to engineer around. So we can make incremental steps. I think right now one of the things we're doing is our detectors are good enough that they can operate on a TEC cooler, and so you know, a lot of our sponsors are just more interested in like, look, we can put it on a TEC cooler. We don't need to carry liquid nitrogen around like on an airplane or into space or something like that. So show us that you can make a focal plane array out of these, right? The other thing that we're doing is we've largely thus far focused on reducing the thickness of our detectors. But I think the next step has to be reducing the lateral dimensions. So reducing the thickness gives you a linear improvement. Reducing the lateral dimensions could give you a quadratic improvement. Still not exponential, but it's better than linear, right? And so one of the things that we're doing with a collaborator, my good friend Victor Podolsky from UMass Lowell, he's designing these like metasurface lenses that we're patterning onto the backs of our detectors. And then we shine light in through the back, and it focuses that light down to a much smaller detector. So instead of having a detector that's, you know, 100 microns by 100 microns, we might have one that's, you know, 10 by 10 microns. So that's a 100x, ideally a 100x reduction in your dark current, which would be a 10x reduction in your noise, which would allow you to go to higher temperatures, right? So, but again, even 100x reduction in dark current, like that's probably 20-30 degree improvement in temperature performance, right? Like that's the battle that you're fighting at this stage. Yeah.
Right, it's a little over time already.
Okay.
So if we can give them a round of applause. If you have any questions, there's still the lunch, right? So I highly encourage you to come, it's great, and ask any questions and have some good food. Thank you. Yeah, I got it.
Thanks, Dan, that was great. See you in just a little bit. Yeah, I gotta sit.
But like, yeah,
There's like class in here after.
Oh.
It's like, oh, we're gonna have to cut it out. We didn't know that before. That was awesome. It's just like, it felt like to some degree for me, like memory lane. You know what I mean? Like I haven't touched, and we'll talk about this. I haven't touched this. I don't know why. I